Hey folks, for today let's talk about binary search. So binary search is a pretty common concept that you'll see in LeetCode and data structures and algorithms. It's a fairly simple, I guess you could say, concept, but for beginners it may not be the most intuitive to implement. So let's go over it today. So to jump into things, the best way might be to start with an example. So let's go to my text editor here. And let's say we're given a sorted list of numbers, right? So it's a sorted list of numbers, I'll just call it, of nums, right? And let's say, just pick a random bunch, but they have to be sorted, and you'll understand why in a little bit, right? So we're given this sorted list of numbers, and let's say we're looking for 3, right? And don't mind this this auto syntax here is because of the text editor, but actually let me just comment it out so it's not confusing with all the syntax and everything. Okay, so let's say we're looking for 3, and what does that mean? It means we can either see if the number is in the list, or we can return the index at which the element exists. The exact definition of like which one, like the either whether it exists or what index to return, that doesn't really quite matter. Like the approach is still going to be the same for binary search, but let's say we're just looking for 3, right? Let's just say for to start with, like, does it exist in the list, right? Looking for 3. So just to clarify, does 3 exist in the list, right? So what's the way that you might approach this? Well, the most common way of approaching this, or I guess the most naive, by the way, I always thought naive was kind of like a bit of like a condescending word, but let's go with simple, right? The most simple way of approaching this question is we can iterate through each element from the beginning in the list and basically just check if that element is equal to what we're looking for, right? So say approach 1 is this. Start from, again, not the most technical definition, but this is more geared towards like high level understanding. So start from the beginning of the list, iterate through each, let's make this a new line. So through each element one by one, just be really clear, and check if the element is equal to 3, right? So this is the most simple way of doing this, right? And this way works, but it's not the most efficient, because if you can imagine, if this list were to be a humongous list, then we have to check each element in the worst case. Let's say we're looking for, say there's a huge number or huge list, and we're looking for an element that corresponds to the last element in that list. So if we implement this way of searching through the list, then it might take a little while, a lot longer than we can theoretically do it. A better approach would be to, because we know that this list is sorted, what if we checked in the middle of the list first, right? Because if we know, let's say in this example, right? Let me pull this down here maybe. Let's call it approach 2. Let's say we're looking for 3. And what if we check the middle of this list, right? So let's say the middle is at 5, right? So you can say roughly kind of breaking this list in half. We have 5. Well, look what happens. So we see that the middle is 5. But we know we want 3. And since 3 is less than 5, and due to the fact that this list is sorted, we know that 3 has to be on the left side of 5, right? Now, left side, we don't really know where exactly on the left side, but we just know it has to be left of the element 5. So what we can do in this case is we've kind of reduced our problem to a smaller section of the list, right? Because now we know that from here to here, 5 to the end of the list, 3 is definitely not there, obviously. So 3 has to be on the left side of 5. So we've effectively gotten rid of all these choices or all these options or these possibilities and narrowed our search domain to basically the first 3 elements here, right? And once we've done that, once we say, okay, 3 is on the left side of 5, that means I can search this part of the list. Then what do we do in this case? Well, this is basically the question that we had at the beginning, right? Which is given a list, sorted list, see if 3 exists in the list, right? But in this case, once we ruled out the top half, we're just left with the bottom half. So we're starting off with a smaller list. So we apply the same logic again to this part of the list. So we look at the middle, which is in this case 1, right? So 1 is obviously less than 3. So that means that 3 must be on the right side of 1, right? So now look, we've gotten rid of the first part up to 1, that part of the list, right? We've also gotten rid of from 5 to the end of the list. So next, we check to the right of 3, but less than 5, which in this case just happens to be 3, right? So once we've done that, we ask again, what is the middle element? Well, in this case, the middle element is just 3 because, again, like we've narrowed our search domain to just 1 element. And the middle of a 1 element list is just the element itself, right? So we check the middle and we know that we find that it's 3. So in this case, we just return 3. So that gives us kind of a good starting point to start implementing this approach, which is known as binary search. So let me be clear here, binary search, right? So effectively what you're doing again is starting with a large list, checking the middle, right? So start with large list, check the middle element, determine which part of the list to search next, right? Let me zoom out a little bit. Right, so that's effectively what you're doing. And you're doing this in you're doing this over and over again, right? Because each part of the list that you've narrowed down, that's like the new list that you're looking at. So basically, let's start with the very beginning, right? So start a large list. So let's say we have an index. Let's call it the start index, just to be really clear. We'll call it IDX is 0, and we'll have an end index, which is, in this case, index 6, which is the last element, right? It points to the last element because this is 0, 1, 2, 3, 4, 5, 6, right? So that's what we're starting out with. These two indices indicate from where to where we're looking at currently in the list, right? So now we check the middle element, right? So we check the middle element. So in this case, the middle element is 5. But you can imagine, let's just extend this list. What if there are an odd number of elements in this list, right? Like in this case, there are, what if there's an even number of elements in the list, right? In this case, there's 8 elements in the list, right? So how do you define the middle? Because the middle could be either 5 or the middle could be 8, right? The middle, I guess, if you look at it visually, is just like this, right between 5 and 8. But in this case, it doesn't really matter because you can define it as 5 or as 8. And for simplicity's sake, like when you're coding it, you can just define it like this. Middle index is start IDX plus end IDX divided by 2, right? Because this is basically taking the average of the start and end index. And so if you can imagine, it's taking an average, so it's taking the midpoint between those two. So in this case, 0 plus 6, 0 plus, let me move my face up, 0 plus 6 is divided by 2 is equal to 3, right? So in this case, the middle will be 0, 1, 2, whoops, 3, right? Which would be the element 5, right? So, I mean, we could define it like this, or we could define it by, divide by 2 plus 1, but we'll just define it by 2 just to be simple, right? As long as we do the same definition throughout the rest of the code, middle IDX here, right? Okay, so that's great. Make some space here. Awesome. So what do we do after we set the middle index? After we set the middle index, we determine which part of the list to search next, right? So how do we do that? Well, think about it. When we check the middle, we're essentially just saying, is the number we're looking for greater than or less than or equal to the number that we're looking for? If it's equal to, that's great. We found an element, right? So, and we return true. But what if it's less than, right? So let's start to kind of code this out pseudocode-wise. So if the middle element, which is basically, let's call it if sort list of nums middle IDX, and let's actually just make this, to keep it shorter, named mid IDX, right? Because you still know what that means. If the middle element is, let's start with the equal case, equal to what we're looking for, equal seeking, then basically we just return true, right? That's great. But if it's not equal to, then if it's less than, right? So if it's less than seeking, right, what are we doing? So if the middle number is less than what we're seeking, that means the seeking has to be on the right side, right? It has to be on the right side of the middle element, right? So that means we effectively gotten rid of the left side of the element, left side of list up to the middle element. So what we can do is, remember, the start and end index represents the part of the array or the list that we're searching for. And since we've gotten rid of the left side, so like, let's say in this case, like we're searching for, right, the middle is 5, right? Let's say we're searching for 10, right? Well, in this case, we've gotten rid of 0 through 5, 0, 1, 3, and 5. So the start index, we move to 8, right? Because we don't care about the left side of that. So what do we do? In this case, that's essentially setting the start index equal to what? Equal to the middle index plus 1, right? Similarly, if the middle element is greater than what we're searching for, we're basically getting rid of the right side of that, the right half, if you will, and including the middle element. And now we're searching for the left half. So similarly, it's a hard word to say, similarly, we set the end index to middle IDX minus 1, right? And actually here we can make this like an else if, right? Else if, because it can't be both cases. And even here we can do like an else if. Not necessary, because this is going to guarantee, if this hits this part, the code hits this part where the seeking element is found, then we just return out of it. So don't really need it. And we can make it simpler. Else, we can actually name it just to comment, just to be clear, right? Because there's no other condition, right? Because if these first two conditions are not met, then that means the last condition has to mean this middle element is greater than what we're looking for. Anyways, let me put this in Python code and just make it easy. Okay, so after we've done the middle check, that's all great. Remember, we need to do this again because we've only narrowed down the list, right? So we need some kind of loop, right? So we need some kind of loop here. Let's just call this like some kind of loop. Again, this is pseudocode that we're starting with, right? So we're doing some kind of loop and we're continually checking this. But as you might be able to think, you might think like at some point this loop's got to break, right? So at what point does it break? Well, it breaks when, let's think of an example here. Let's go to like a simple example, right? Well, first of all, it'll break when we find the element that we're looking for, right? But what if the element's not there, right? Let's say we're looking for another example. What if element is not there, right? Because according to this pseudocode we have here, if we find it, it will return true. But if we don't find it, it's gonna, we need to exit out of the loop. So we're probably going to need some kind of conditional in the loop to account for the case when we don't find it. So what happens if we don't find it, right? So let's look at another list. Let's say list is 0, I just say call it 0 and 1, right? So in this case, let's say we're seeking for 2, right? Okay, so let's look at what happens here. So, all right, so starting with, we'll just have to do a dry run. So start is 0, start AX is 0, and IDX is 1, right? And then the mid IDX is 0 plus 1 divided by 2, which, if we run this in Python, is just going to equal to 0, which is going to be this first element. So that first element is going to be the middle element, right? Okay, so let's follow this logic here that we, according to this above. So the middle IDX, the middle element is 0. 0 is less than 2, which means at the next loop, next part of the loop, start index is going to be, according to our logic up here, is less than seeking, right? So that means start index is mid IDX plus 1, which is 0 plus 0, whoops, 0 plus 1, right? And the index doesn't change, right? Because we're only narrowing the element from the start index, right? So now the start index and end index are the same, right? And this is something that I actually didn't account for up here, but actually this code kind of handles nicely, is that at some point, if the element is not in the middle, at some point we're going to run into the case where the start index and the end index are the same indices, right? The same element. In that case, the middle index is just the element that that list contains, which is like a one element array, right? So in like in this case, like the start index is 1 and the index is also 1. So we're only looking at a list of length 1 that contains one element, right? So the middle element of that list is just the element itself. So that nicely checks that case, like the one element case, like when it's only length 1 element long. So in this case, the mid IDX, like I just mentioned, is 1 plus 1 divided by 2, which is just 1, right? So, and now we check, is the middle element equal to 2, which is not. So again, the start index is going to be 1 plus 1 is 2, and index stays the same. And at this point, you're going to start to see, okay, this is looking a little weird now, because the start index is greater than an end index, how does that make any sense? Well, this is going to be what happens when we can't find an element. Like when we can't find an element, the start index is going to be greater than an end index because we're effectively resetting the start index to one after the middle index, but the middle index is equal to the start index, right? Like in this case, the middle index is equal to the start index. We still haven't found it, but we're going to like change the start index in this case. So that's guaranteed to make it greater than the end index, right? So really this loop actually, this part of the code actually works out pretty nicely. It's going to be while the start index is less than or equal to the end index, right? So as soon as this part doesn't make sense, that means we've reached a point in the list where we checked as much as we can and we're basically done, right? So at this point, we can break out a loop, and at the very bottom of the code, we can return false, right? So this is essentially binary search, right? Oh, I should say from the beginning, actually, it doesn't matter. I was going to say, what if there are duplicates? Okay, even if there's duplicates, it doesn't matter because, like, what if we had 0, 1, 3, 3, like a bunch of threes, you know? In that case, it doesn't matter because how we define this question is, does it exist in the list, right? This problem might be a little harder. I think if we phrase the question in a different way, like let's return the index of the first place where like 3 exists, right? Like if we had 3 here, like we want to return index 2 in this case, right? But our situation is very simple. It's like we just return if it's even in the list, right? So we don't need to worry about that. Sorry for a tangent there, but that we can save that for like another question, another day. Yeah, so like we can start implementing this, I think. And we had like the bulk of the pseudocode done up here. So let me comment all this out and let's just start writing the function with def binary search. It takes a sorted list of nums, just call it that. And I'll basically copy and paste this part because we can just do some minor changes on this. All right, so start index. Okay, another thing and this is okay because pseudocode gives you like the foundation, and you kind of have to like, you know, write around it and stuff. But that's fine, you know. So basically, inside the loop, we're setting the start index and the end index, right? Or sorry, we're setting the middle index, right? So we're moving this average check into the middle or inside of the loop. So start index is always going to start as 0, and end index is going to start at the last element, which is length of the list minus 1, right? Okay, so let's take a look at this. Yeah, so let's run some test cases. Let me down here. Let's say test list 0, just to be very explicit. 0, 1, 2. Expected result. I'm going to write this in a way that's kind of you know, friendly to kind of unit tests. So expected result is searching for seeking is 2. Expected result is true, right? So in this case, if we run the code, we expect. Actually, let's go ahead and just call it test list so we can reuse this code. Test list is equal to expected result, right? So this will kind of give us a list of, hopefully a list of trues. I'm just running out a bunch of test cases again, right? 0, 2 is, expected result is false, right? In this case, whoops, gotta capitalize that guy. True. 0, 2. In this case, it expected to be true. right? And let's test like an empty case, right? Empty case is false, right? So let's go ahead and run all these. And again, we expect there to be a bunch of trues, right? So true, 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 true. Okay. Let me go to my terminal. Let's run, I think it's Python main.py. Let's see if we have any bugs here. Ah, okay. So we have a bug here. Invalid syntax. Is it else if? Sorry, I think it's else if. I actually don't code. During the day, I work full-time software engineer. I don't code like, using Python. So, true. Okay. Where is true? What's the name? Global name true is not defined. 61. What? What is it saying? Global name true is not defined. Is it like this? So I'm not a Python expert. I haven't done Python in a while, actually. What? Expected result is true. Interesting. Oh. I'm dummy. True. Try this again, shall we? There we go. Nice. Yeah, basically had to capitalize the keyword. Okay. So yeah, that works. Yeah, so that's essentially binary search. The TLDR is, there's a couple of points that I think I would recommend obviously implementing this yourself. I think over time, there's a couple of things that are important. One is the fact that you have to update the start and end index depending on what the middle element is compared to what the element that you're looking for, right? So that's one thing. The second thing is, how do you break out of the loop? This isn't the most intuitive thing, which is to check that the start index is less than or equal to the end index. But I guess it kind of makes sense, right? Like at some point, if you go through all these operations, you're continually updating the start index and the end index. At some point, if you never find the element you're looking for, you're going to search for a part of the list that doesn't really make sense, right? Like your bounds are gonna kind of cross each other, right? So I guess in that sense, it kind of makes sense, but this is another important part, which is, obviously, like, how do you break out a loop? All right, guys, so that's essentially binary search implemented in Python. Let me know if you have any questions in the comment box below. Hopefully this was a good intuitive explanation of how binary search works. You'll definitely, like I mentioned earlier, encounter this in your LeetCode questions, and some languages have like a built-in library where you can just call like a search function and it will perform a search for you, but it's definitely good to know how to implement this on your own. So thanks for tuning in, guys. See you next time.